The last section of 1.3 has to do with piecewise functions. A piecewise function is a function where the rule that determines the output for the function is changed based on where in the domain your input value is, okay? So I know it says two or more equations. I don't really like the use of the word equations here. Really, I think expressions is probably better. It's not two different functions. It's a single function, so it's just y or f of x equals, and then we're going to have maybe one rule here and then a specified domain, okay? And then maybe a second rule and then another specified domain. And these could be written as inequalities, equalities, that kind of thing, or intervals. And there could be multiples of these, but essentially we are looking for kind of a combination of more than one function, but there is only one function total, okay? So let's look first at evaluating piecewise functions, okay? So the first thing we need to do is we need to look at our input value and determine which section of the domain does that input belong in, okay? And then that tells us which rule we're going to use for evaluating. So for example, with this up here, if I'm looking for like f of, I don't know, 7, and 7 is in this piece, then I'm gonna plug 7 in as the input into this part of the function. Again, not two different functions, but we'll plug into this part, okay? So here we have a function c of t equals, and so it's 20 when t is between 0 and 60. Notice that these are inclusive, okay? And then greater than 60, we use this rule down here, okay? So if I want to evaluate c of 40, okay, my function here is c, 40 falls inside this domain, so then that is equal to 20. Okay, and also just in general, not just for the section or chapter, but just really anytime you do math, I'm going to really encourage you, don't write an expression or a number or something like that that's not attached to something else. Like it's like, I don't want to just write a 20 here. I mean, yes, technically that is the correct answer, but I want to say that this is equal to 20 because I'm assigning it a value. So really I'm defining this as equal to 20, okay? It makes me better at communicating in mathematics, and it makes my work easier to follow for whoever is reading it. And it makes me more likely to be able to follow it myself, okay? So, I mean, there was not a lot to this problem, but that's just my general encouragement for you. Okay, so for c of 80, the input value falls into t greater than 60, so this is going to be equal to, and then I'm going to write this expression and plug 80 in for t. So it's going to be 20 plus 0.4, 0.4 is 2/5, and I'm not using a calculator here, so I'm going to write it as a fraction, but if you're using a calculator, hit that 0.4, doesn't matter, times 80 minus 60, okay? And then this is equal to 20 plus 2/5 of 80 minus 60 is 20, okay? And then 2/5 of 20, let's see, so we've got 20 plus is 8, so this is equal to 28. Again, it's fine if you use a calculator, I just don't have one with me. Okay, for number 2, same kind of deal. If you want to pause and go ahead and try one, that's fine. So here we have our domain is divided at 0. So for less than 0, we use 6x minus 1 for our function, and greater than or equal to 0, we use 7x plus 3. Okay, and by the way, the domain does not always have to be negative infinity to positive infinity. So we could have just like x is between 0 and 5, and then x is between 5 and 20, and then the total domain is just 0 to 20, and that's all there is. That's okay. But here, usually we have negative infinity to positive infinity represented between the total of these. Okay, so f of negative 3 is equal to, so negative 3 is less than 0, so I'm using the top one, 6 times negative 3 minus 1, which is negative 18 minus 1, negative 19. Okay, f of 0. Now, f of 0 falls into this domain because this does have the or equal to part of the inequality symbol. So I'm doing 7 times 0 plus 3, which is 3. Okay, move that down since I have this room here. Okay, f of 4 is greater than or equal to 0, so I'm using the bottom part of the piecewise function. So 7 times 4 plus 3, so 28 plus 3 is 31. okay? Got another example here. Now, here, the domain's written a little bit differently. There's still no values that can occur in more than one piece. In 1.2, we talked about functions specifically, and we said one input can't have more than one output. So here, for example, if I were to say this is when x is less than or equal to 0, and this is greater than or equal to 0, 0 would fall in both of those domains, but I would have a different output. That would mean it's not a function, okay? But since this is a function, we can't have any overlaps. The top part of the domain, of the function's domain here, says x is not equal to 4. So for any input other than 4, sorry, the spacing is a little wonky here. Okay, for any input other than 4, I plug into this value right here. All right, now if I were to try to plug 4 into this, I see that I would have division by 0, which I can't do, so that would not exist. But if x is equal to 4, that sends me down to this part of the domain, and so my output is just 8. Now, it doesn't look like a function or an expression, but it is just, think about the graph y equals 8. It's just a constant function with a height of 8, so it's just this, but it's only at the point when x equals 4. So the rest of this, actually I'll just do this, the rest of this does not exist, well, that's my increment, only that ordered pair at 4, 8, and then whatever we get from the top graph. Okay, so for g of 4, we plug 4 into this right here, output is the constant 8. Okay, for g of 0, which is not equal to 4, I'm plugging in up here. So I'm going to have 0 minus 16 over 0 minus 4, negative 16 over negative 4 reduces to positive 4. And then for g of 6, this is equal to, so 6 squared, 36, minus 16 over 6 minus 4. Okay, so I have 20 over 2, which is 10. So g of 6 equals 10. Okay, last piece here is, last piece of piecewise functions is graphing the piecewise functions. And here we're basically graphing two functions simultaneously. I mean, it's only one function total, again, but we think of it as two separate equations and then only graph them over their associated domain. So this right here, f of x equals 3. F of x equals 3 is the same as y equals 3. So again, that's the constant function y equals 3. But instead of, don't write this down, instead of doing this, I'm only going to draw the part that exists where x is less than or equal to negative 1. So I'm going to start over here at negative 1. I do need to put increments on here in case I was counting by 2s or something. Okay, and so instead of this, I'm going to start with, and I do have a closed circle because that point is included, and then I only graph this side of the line y equals 3, okay? And then to the right of negative 1, so starting from negative 1 but not including that, we're going to use an open circle, I have the line y equals x minus 2, okay? Now, as far as how you want to graph this, you've got a couple of options. Some people would prefer to just graph y equals x minus 2, which is a line with a slope of positive 1 and a y-intercept of negative 2. So they would prefer, prefer to just do this, okay? And then go back and say, wait a second, I can only use the part that's greater than or equal to 1, and then just go back and erase things, okay? Which is kind of what I did on that y equals 3. The other option is plug negative 1 into this function to see where you're starting, like your end point of that piece of the piecewise function is. So if I plug negative 1 in here, in other words, I'm evaluating f of negative 1. Now, I know that negative 1 is included up here. This is going to be an open circle, okay? I'm going to have negative 1 minus 2, which is negative 3, okay? So I have an open circle at negative 1, negative 3. This point does not actually exist, but I'm going to have everything up to, but not including that. Okay, and then what's the slope of this line? The slope is 1, so I'm going to count up 1 over 1, get my second point, and that's enough to draw this. Okay, so you could draw the whole thing, or you could just draw the end point by plugging negative 1 into the bottom part, and we get this. Now, really, this is a little misleading. F of negative 1, like the actual function, is not negative 3. It's positive 3, so maybe don't write that as part of your answer, but it does help me figure out where to start. Okay. All right, this one, g of x, negative 1/2 x squared when x is less than 1, and 2x plus 1 when x is greater than or equal to 1. Okay, so again, I can start by just saying what does the whole function look like, negative 1/2 x squared everywhere, and then I could just erase the part that's bigger than 1, or I can plug in an endpoint. So I'm going to take 1, plug it into this function, kind of do a combo of these. If I plug 1 into this function, I get negative 1/2 times 1 squared, so just negative 1/2. So at 1, negative 1/2, I have an open circle because we are not including that. Actually, I'm going to make this graph a little bit bigger because why not? Okay. So if I'm going to count by ones, I should have put more increments on the other graph. That's okay. If I count by ones, I have a point at 1, negative 1/2. Oh, nope, open circle. Okay. And then this is a parabola that opens downward. It still passes through the origin, okay? And because of this negative 1/2, it's a little bit wider than a normal parabola. Now, if you don't remember all the transformation stuff, not a big deal. Stick in your calculator, that's fine, okay? But I'm gonna do it based on what I know the graph of that to look like. So this parabola, I'm gonna plug in negative 2. Okay, I'm picking negative 2 because when I divide by 2, I want to get an integer. So if I plug negative 2 into that, g of negative 2, I get negative 1/2 times negative 2 squared is positive 4, which is negative 2. So I have a point at negative 2, negative 2. Okay, so I have a parabola right here. Again, not to the right, because then we switch to this domain, but that's what the left side looks like, okay? And then when I plug 1 in here, g of 1 gives me 2 times 1 plus 1, so 3. So 1, comma 3. And this is a closed circle because we include the 1. And then this is a line with a slope of 2, so up 2 over 1 to get a second point, and I'm just drawing that piece, okay? We could also just lightly draw a y-intercept at 1 and then a slope of 2 and then draw the whole line and then erase. Either way is totally fine. Okay. All right. So that is piecewise functions. This last piece here for 1.3 is functions and difference quotient. A difference quotient, this is not negative. This should be a colon. Sorry guys, I did not proofread these notes super well, so some typos. Okay, so that is not a negative. So a difference quotient, think about what these two words mean. Quotient means we are dividing, difference means we are subtracting. So it is we subtract and then we divide. Now, there's nothing being subtracted in the denominator, but difference quotient comes from an expression that actually looks like this, where it's x plus h and then minus x. X's cancel out, you just get the h. You don't need to see that. This is what we end up with, and this is the expression that we're going to be evaluating, okay? It does clarify that h cannot be 0, otherwise we would have division by 0. Actually, we would have 0 over 0, okay? All right, so we've done some evaluating functions. We did that in the last videos. So let's look at this, and we are going to take x plus h. That becomes the input, and this whole expression gets plugged in anywhere I have an x. So this is equal to negative 2 times the quantity x plus h squared plus the quantity x plus h. I don't really need this set of parentheses, but it's not, it helps me remember to do the whole thing, and then plus 5, okay? Now we need to simplify. It's still going to be in terms of x and h, but we don't want to have this, like this, this binomial squared and this one here. We'll combine like terms. Okay, so we have negative 2 times, and then x plus h squared is x squared, come on pen, plus 2xh plus h squared, and then plus another x plus h plus 5, okay? Then equals, see I'm still using equal signs to connect this. I'm going to distribute the negative 2, so negative 2x squared minus 4xh minus 2h squared plus x plus h plus 5. Lastly, combining like terms, I have a negative 2x squared. Actually, no, I don't have any like terms, do I? Nope, back up. Done. Okay, I don't have any like terms because I can't combine like x squared and h squared, and this has an h, this one doesn't, this one has, yeah, so this is it. That is fully simplified. Okay. So now for this one, we're doing a little bit, you see that, a little bit more with it. So it's f of x plus h, which we actually just evaluated, so we don't need to write that out again, minus f of x, the original function, all divided by h, okay? So this is equal to, and again, I'm just going to copy this from part 1. So negative 2x squared minus 4xh minus 2h squared plus x plus h plus 5. Okay, so that's the f of x plus h minus f of x. Now, I will tell you that this is one of the most common mistakes that gets made with this type of expression, not distributing a negative, okay? What frequently happens is we see, oh, okay, we're subtracting that. All right, so that negative becomes a positive, 2x squared plus x plus 5. Nope, wrong. Don't write that, okay? It should be minus, and then use parentheses, the entire quantity, negative 2x squared plus x plus 5, okay? This negative has to be distributed to the entire expression f of x, which I'll do in the next step, and then the whole thing is over h. Okay, so I'm going to go ahead and switch colors to distribute that. Okay, so this will become plus, this one will become positive, negative, and negative. Okay, so now I have a negative 2x squared, and this is now plus a positive 2x squared. Those cancel each other out. Okay, and then I have a negative 4xh. I don't have another xh term, so that term is still present, negative 4xh. Okay, and then, so I've used that one. And then negative, I don't have any other h squared, so minus 2h squared, okay? This x, I have a positive x, and now this is minus x, so those cancel each other. And then this h is by itself, so plus h. And then we have a 5 and a negative 5, 5 and negative 5, okay? Cancel each other out. And then that whole thing is still divided by h, okay? For simplifying, I see that every term in my numerator has an h, so I can factor that. And I'll have h times negative 4x minus 2h plus 1, all divided by h. And then when I reduce this, let me come down here. I'm left with just negative 4x minus 2h plus 1. Okay, so that's my completely simplified expression. Now, this is a particular difference quotient that is, it gives us the definition of the derivative, so it's a calculus concept. We're not going to be using derivatives here, but this is just kind of practice on the difference quotient, the expression that gets us to that. On this step right here, if you do not have an h in every term in your numerator, you need to back up because you did something wrong algebraically, okay? If this difference quotient for any function, if this difference quotient is written out correctly, you will always be able to reduce the entire numerator and the denominator by that h, okay? So we won't have an h left over in our denominator. We still might have one up here, that's fine, but we won't have one in the denominator, okay? So that's kind of a way to know, it's a little bit of a red flag where you can say, wait a second, I'm supposed to be able to reduce this whole thing by h, so something must be wrong, okay? All right, so I would suggest that you pause it, and then we're gonna try one more of these. Okay, so new function, f of x equals 1 over x. We're first looking for f of x plus h. So this is equal to 1 over x plus h. Bam, done. Okay, that's it. There's nothing to simplify there, so we just leave it. Okay, now we're going to take that, subtract the original function f of x, divide the whole thing by h. So this is equal to, so f of x plus h, 1 over x plus h, minus f of x, 1 over x, all over h. Okay, for simplifying, we can do this a couple of ways. We can get a common denominator. These do not cancel out, okay? Those are denominators. Just like I can't, like if I have, let's say I have 1 over 7 minus 1 over 3, I can't say, oh, that's going to be 1 over 4, let's just subtract these. No, bad math. Okay, I could get a common denominator, and then I could write the dividing by h as like times 1 over h, and I could go from there. But really, what I think the simplest way to get rid of these complex fractions, complex fraction means a fraction inside a fraction, is to figure out the least common denominator of your inside fraction. So in this case, it's always going to be the 2 on the top, and then multiply the entire fraction, the big fraction, by that over itself. So I've got an x plus h and an x. Let's do, what have we done? Let's do whatever this color is. Okay, so I've got an x plus h and an x. So my least common denominator is x plus h times x. It is not just x plus h. Just like over here, my least common denominator would not be 7. It would have to be 21 because I need it to be divisible by both 7 and 3, okay? And I'm going to multiply on the top and bottom by x plus h and x, okay? The reason I'm doing this is because when I distribute this whole thing to both terms in the numerator, which I need to, both of these smaller denominators will get canceled. So if I have 1 over x plus h times x plus h times x, the x plus h cancels out and I'm left with 1 times x. Okay? And then 1 over x times x plus h times x, now the x's cancel out and I'm left with x plus h. Be very careful about the negative though. Like I said, most common mistake is forgetting to distribute that. And then down here, h is not over anything. It's not like h over x or something, okay? So there's nothing to be reduced, so I just have this times this times this. So I have h times x plus h times x. Don't worry about distributing that because remember what I said up here? You always should be able to reduce an h out of the entire numerator to cancel it with the h in the denominator. So I'm going to leave that factored because I'm going to cancel it anyway. Okay, so now if I distribute this negative, I have x minus x, which is 0, and then minus h, so this is a negative h, over h times x plus h times x. And now I can reduce that. It doesn't disappear. It's not a 0. Okay, it's a negative 1. So I have negative 1 over, at this point you can leave this factored. That would be my suggestion, honestly. I don't know if this is something Pearson cares about, but if you want to distribute, you would have negative 1 over x squared plus h times x.